Today we're going to cover section 5.6, vectors in space. One of the things that's interesting about vectors in space is that we are now talking about three-dimensional things, and so since we're talking about three-dimensional things, it's important that we understand the orientation. And so these first two pictures that I have here are demonstrating exactly that. This one with the hand on it is showing the x, the y, and the z in the positive direction, so you can see it. And then the other one on the left is demonstrating the grids with some numbers on it. But you can see that again, this is positive, and going up is positive. Now that we've kind of got that in the orientation, let's go ahead and use some of this information to be able to solve some problems. The first thing that we're going to talk about is the distance formula. And so since we have three values, we need to have x, y, and z. We need to find the distance in x, y, and z. And so the distance formula that you've used in the past has only had x and y, but now we need to introduce z. So let's go ahead and do an example with this so you guys can see it. And so here's point 1 and point 2. And so to find the distance, I'm going to take the square root of the differences from the second point to the first point. That quantity squared, that's the x's, right? The 4 minus the negative 1, plus the y's. So it's going to be negative 2 minus 3, that whole quantity squared. And then plus 5 minus 2 and that quantity squared. So that's going to give me a distance of 5 squared plus negative 5 squared plus 3 squared. And so that's still under the square root. So the distance will be 25 plus 25 plus 9 under the square root. And so the distance that we have for these two points, the distance between them is going to be a distance of 59, square root of 59 units. So whatever the units that are being used would be. Very, very straightforward. It's just like the problems that we've done in the past. It's not a big deal. Okay. Another way to write vectors, so you've seen vectors written with this kind of notation, right, where we have A, B, and C. Now what we're using is I, J, and K, and I, J, and K are vectors where I is in the x direction, J is in the y direction, and K is in the z direction. So it's just another way of writing those. And so this is how we do it. Here's a theorem for us to look at. So we can write vectors. If we have 2 points, the direction of the vector matters. So we can see here it's going from P1 to P2. So that's what that arrow means. It's telling us in which direction it's going. And so since it's going from P1 to P2, we're going to subtract the distance from the second point minus the first point. So let's look at this example that we have with our P1 and P2. So we're going to let V equal P1 to P2. And the way we're going to get this is we're going to go 4 minus a negative 1, and we'll call that I, plus 6 minus 2, J, that's the direction it's going in, plus 2 minus 3, K. And so we're going to clean this up. We're going to get 5I plus 4J minus K. And so this is the vector V of these 2 points that we just did. So it's really pretty straightforward. It's just a matter of getting these formulas down. And like I said, for this exam, I'm going to let you guys use as many notes as you'd like. Okay. These are some formulas that if I was you, I would jot down and have. It's important that you understand and are able to use these. I'm going to use them right now in order to be able to demonstrate an example for you guys, but I wanted to leave it here for a little bit so that you guys could maybe pause the video and write these down so that you have them. It's going to be very beneficial. Alright, so let me do this v plus w one first. So v plus w is simply going to be 2i plus 3j minus 2k plus 3i minus 4j plus 5k. And we just add the things that are similar. So I'm going to go 2 plus 3, 2 plus 3i, not j. 2 plus 3i plus 3 minus 4j plus a negative 2 plus 5k. And so that's going to give me 5i minus j plus 3k. And that's what v plus w would be. V minus w is going to follow the same principles, but I'll write it down so you guys can see. And instead of addition, we're going to subtract, so that's going to change the signs on this side. So we're going to end up with 2 minus 3i plus 3 minus a negative 4j plus a negative 2 minus 5k. And so that's going to give me a negative I plus 7j minus 7k. And there's that vector. It's that straightforward, that simple. All right, let's show one with a scalar. So all the scalar is going to do is it's going to multiply the vectors first, and then once we've multiplied by the vectors, we'll subtract them. So I'll go 2 times 2i plus 3j minus 2k minus 3 times 3i minus 4j plus 5k. So that's going to give me 4i plus 6j minus 4k minus 9i plus 12j minus 15k. And that's going to clean up to be a negative 5i plus 18j minus 19k. So all the scalar does is multiply it, and then we add the vectors like usual. So the scalar is just basically saying whatever vector v's length is, we're going to triple its length. That's it. It's that simple. Okay, the unit vector, this is a formula that you should know. We're going to do an example with it, but basically if we have a vector v, the unit vector is just going to be the vector v itself divided by its magnitude. So here is an example that I'm about to do. So the first thing that I'm going to do is I'm going to find the magnitude of v. And so we should remember that the magnitude of v is just basically each component squared and under the square root. So this is how we find the magnitude. And so that's going to give me 4 plus 9 plus 36. And so it's going to be square root of 49, or basically 7. Okay, so then our unit vector is going to be equal to the vector v divided by 7. So when I rewrite it, u is going to be 2/7 I minus 3/7 j minus 6/7 k. This would be the unit vector for this vector v. Again, like I said, very, very straightforward. Here's a definition for us, and it's the dot product. And we notice that the dot product, what it's doing is it takes the I components and multiplies them, plus the j components and multiplies them, plus the c components and multiplies them. So here's a quick example. So v dot w is going to be 2 times 5 plus a negative 3 times 3 plus 6 times a negative 1. That's going to give me 10 minus 9 minus 6, which will give me a negative, let me make sure I get this right, negative 1, so that's a negative 5 is the answer. Negative 5 would be the dot product of this. Now, one important thing about the dot product that you should know and remember is that if the dot product is 0, we have orthogonal vectors. And orthogonal means they're perpendicular. So if v dot w is equal to 0, v is perpendicular to w. That's something that is important to remember and know. It should be useful. Okay, we know that the dot product is commutative and the dot product is also distributive. So that's important to know. And then the dot product is basically the same as the magnitude squared. And then any dot times 0, the 0 vector will be 0. All right, here is how to find angles between two vectors. And so to do this, what we need to do is we need to take the dot product and then the magnitude of each of the vectors that we have. So first in this example that I'm going to do, I'm going to take the dot product of u times v. And so that's going to be 2 times 2 plus a negative 3 times 5 plus 6 times a negative 1, which is going to give me a negative 17. Now the magnitude of u is going to be 2 squared plus a negative 3 squared plus 6 squared under the square root. And that's going to be square root of 49, which will give me a 7. And then the magnitude of v is going to be 2 squared plus 5 squared plus a negative 1 squared. And that's going to give me square root of 30. So then cosine theta is going to be a negative 17 over 7 radical 30. Let me write that a little bit nicer. And so we can find theta by going cosine inverse of a negative 17, 7 rad 30. And that ends up being approximately 116.3 degrees. You'd obviously use your calculator to be able to find that. And this would be in degrees when you go to look for that. Here's something important that I do want to talk about with you is direction vectors. And so when we're talking about direction vectors, direction angles, with vector, there's 3 angles that are measured. And here's what it looks like. The alpha vector is going to be it's going to correspond with the vector with the x-axis. That's this guy. So you can see it's going in this direction. And it's going the angles along the plane. And then beta is with the y, and you can see that it's going from the y vector up to the vector v. And then you can see that gamma is going from z to it. Now, but these are 3 different, it's 3-dimensional, so it's kind of hard to picture. That's why I provided this picture for you guys, but take a bit of time to look at this. One of the things that's important with this is that you note that there are restrictions. So alpha is from 0 to pi, beta is from 0 to pi, and so is gamma. All 3 of them will fall between 0 and pi. Okay. Let's do an example to see if we can find an angle. And so we need to have the magnitude right? Because if we see the formula again, we're going to need the magnitude of v for all three of these angles. So let's go ahead and see if we can do that. And so if we find the magnitude of v is something that we've done now enough. It's -3 squared plus 2 squared plus a -6 squared. And so that's going to be 9 plus 4 plus 36 under the square root. And that's going to work out to 49, which is going to give us 7. Now, cosine of alpha, remember, is going to be the a, which is -3, over the magnitude, which is 7. And so we know that alpha will be equal to the inverse of 3 over 7, -3 over 7. And that's going to tell me that alpha is 115.4 degrees. Now, cosine of beta is going to be my b, or the 2, over 7. And so beta is going to be cosine inverse of 2 over 7. And so beta will be 73.4 degrees. And then for gamma, I think you've kind of seen the pattern now. It's that -6 over 7. And so gamma is going to be cosine inverse of -6 over 7, which gives me gamma to be 149.0 degrees. And that's how we find the angles. So once you have the magnitude, it's just your A, B, and C. Cosine of alpha, beta, and gamma over A, B, and C for each one respectively. And then you can use your calculator with the inverses to be able to find those answers. We can also do it this way, where if we have a couple of the angles, we can go ahead and find it by using cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. So I'll do an example for you real fast just so you guys can see. So using that formula, I'm going to go cosine squared of alpha, which we know is pi over 3, plus cosine squared of beta, and we know beta is also pi over 3 in this example, plus cosine squared of gamma, which we don't know, is equal to 1. And so we're trying to find this. Now, there's some important information in this problem. They're telling us that our gamma is acute, and so it's acute, that means it's less than 90. So we're going to use that information in just a bit. So I know that cosine of pi over 3 is 1/2. So I'm going to go 1/2 squared plus, again, it's going to be 1/2 squared plus cosine squared gamma is equal to 1. So I'm going to get 1/4 plus 1/4 plus cosine squared of gamma is equal to 1. So then cosine squared of gamma is going to be equal to 1/2. And then the square root of that is going to be radical 2 over 2, but a plus and a minus, right? So then gamma is going to be equal to cosine inverse of radical 2 over 2, or gamma will be equal to cosine inverse of negative radical 2 over 2. And so gamma here would be equal to pi over 4, and over here it would be equal to 3 pi over 4. And so from these two, oops, I have these switched. No, that's right, I have it right. So since it needs to be acute, this is clearly not acute. That's too big. So this would be our answer. It has to be the pi over 4 one because of the acute piece. Okay. We can also write vectors in terms of their magnitude and direction. So if you want, you could go cosine alpha I plus cosine beta j plus cosine gamma k times the magnitude. That would give us the same thing. So in the example that we just did, I could have done it as, if I had the magnitude of the vector, I'd be able to write it in this way. It's just information for you to know, but it's just another way to be able to write it. As always, I hope this has been beneficial. All the best.